Mic unmuted. Mute your mic. Dang it. I'm going to track you down and find you. Ryan. Ah. You are now muted. You are the weakest link. Goodbye. All right, let's get back to it. Stonks. All right, last time in lecture. We were talking about how to reduce your stiffness and compliance matrices into forms that utilize engineering constants. So it would be writing these compliance and stiffness matrices in terms of engineering constants. Okay. The method that we have here is that we sort of did like a mock experiment in each one of the general directions where we like just applied stress in the one direction, just applied stress in the two direction, three direction, or just applied shear stress 1, 2, 1, 3, or 2, 3. That was the general methodology. And so if we sort of just like isolate one of the general conditions, for example, apply only sigma 1, you would have something like your full strain vector being equal to your compliance vector S times your full stress vector. In full form might look something like E1, E2, E3, gamma 4, gamma 5, gamma 6. It's going a little bit quickly here, equals to this sort of 6 by 6 S matrix multiplied by only sigma 1 and then all zeros here. That would result for us in something that looked like the following. I'll just write these directly. Epsilon 1 is S11 times sigma 1. Epsilon 2 is S12 times sigma 1. And epsilon 3 is equal to S13 times sigma 1. All right. That's kind of what pops up if we just run this sort of like singular experiment. And then our general idea here is if we want to look at, let's say, this guy over here, you might expand this and say that, okay, we know that our modulus in the one direction is simply the stress divided by the strain in the one direction. So we might simplify this down to show that S11 is simply 1 on E1. Okay? And that was just like one entry of the compliance matrix that we could write in our more traditional like engineering constants that we sort of know and love from your 2004 and 3005 classes. Okay, so that was one example. And the idea here is that we did this for many experiments. Whereas Homer says, asparagus. Yeah, that's probably before your time. Many experiments. And the idea here is that we could isolate what this S matrix would look like specifically for orthotropic, transversely isotropic, or isotropic materials. So could show S for orthotropic materials as the following. And this would be good to sort of write down and actually have a copy of in your notes. Let's make sure I get this right here. Okay, try to do this the best I can. 1 on E1, negative 1, 2 on E1, negative new 1, 3 on E1, 0, 0, 0. So that's from running the experiment like in the one direction. You could also have negative nu 2, 1 over E2 on E2. Here we have negative nu 2, 3 on E2, 0, 0, 0. That's from like running an experiment in the two direction. Continuing, negative nu 3, 1 on E3, negative nu 3, 2 on E3, and 1 on E3, 0, 0, 0. Continuing on, is it G12? No, G23. Oh, sorry. There you go. So this is the compliance matrix written in terms of engineering constants that we're kind of more familiar with. And this is about where we left off last time. Right. One last thing about this particular matrix that I sort of like implied or we've kind of said before is that the compliance matrix and the stiffness matrix, both of these are symmetric, sort of about the diagonal. And so what that means is like after we run our experiments, we have a couple of additional pieces of information that we sort of gather, okay? And what we sort of know to be true is that, let's say, this entry here is equal to this entry here, right? I'll color coordinates for prettiness sake. This entry here will be equal to this entry here. And like this entry here is going to be equal to this entry here, all right? So all of these things should sort of equate to being equal to each other, just sort of by the symmetry of what we know about this compliance matrix S, is that it's symmetric about the diagonal. Obviously, these guys are symmetric as well, right? All these zeros are also symmetric. I'm not going to sort of show those. Those are not really that interesting. But these three here that I highlighted are particularly interesting. And they sort of lead to an interesting finding, all right? So I wanted to show that and make sure that we demonstrate that information just one last little bit. So sort of lastly here, we note that because this Sij matrix is symmetric, we have things like S12 equals S21. Or if we write this in terms of our engineering constants, which we have just kind of done before, this would be like negative nu 1, 2 over E1 is equal to negative nu 2, 1 over E2. Okay? Interesting. Now, I want to remind you that in general, E1 and E2 are not equal to each other for an orthotropic material. So they're generally not equal to each other. And also nu 1, 2 and nu 2, 1 are also generally not equal to each other. All right? So got to keep that in mind. This here is the relationship negative E2 over E1. That's generally what that Poisson's ratio stands for. This here is the other way, negative E1 over epsilon 2. Okay, so generally they are not the same. So we have to keep that in mind when we're working through this or moving through this. Okay. So this is one example. You could see this other sort of example manifesting itself with like the 1, 3 and the 3, 1 entries. Or here, this is like negative nu 1, 3 on E1 equal to negative nu 3, 1 on E3. Clean this up a little bit. And lastly, if we look at like the 2, 3 entry and the 3, 2 entry of S, we'll have like negative nu 2, 3 on E2 is equal to negative nu 3, 2 on E3. Okay. Hopefully you're seeing a pattern emerge here. And you can sort of notice that this pattern is somewhat easy to follow, but there's a pattern here. And that pattern here we generally call the Poisson modulus reciprocity. So this is the modulus Poisson reciprocity. Spelling is hard. And that generally says for an orthotropic material, that this general relationship, nu ij over ei is equal to nu ji over ej. That is your modulus Poisson reciprocity. All right, that's one last little bit of information I had to get in there. All right, good things, good things. Last time we also made simplifications for transversely isotropic and isotropic materials. I'm not going to go over them again. I just remind you that we did do that. And we showed that we reduced from orthotropic material having 9 constants to a transversely isotropic material that has 5 to an isotropic that had 2. Is transversely isotropic has 5 material constants to fully define its behavior, and then fully isotropic, we know 2 constants. And we kind of showed what those matrices might look like with those individual constants present. All right, so those are things we covered last time. Okay, interesting. Here's the rub. We have described all of these matrices in their principal coordinate systems. What do I mean by that? Well, in each one of these matrices, we sort of assumed that our loading is only along the 1 direction. Our loading is only along the 2 direction. Our loading is only along the 3 direction. So we can sort of define each of the individual compliance and stiffness matrices in their principal 1, 2, 3 axes. Okay? Let's make a note of that. So far, we've defined Sij and Cij in principal material axes, like your 1, 2, 3 axes. And we've sort of only assumed that load would be in like the 1, 2, or 3 direction. But we know in general that the loads that are applied to a composite material or an orthotropic material are not always going to be aligned with the one direction, the two direction, the three direction. Okay, so the loads on an orthotropic material may not be aligned with principal material axes. So maybe let's put a picture to this to sort of really clean it up. All right. So assume that you have some cube of material. And it's orthotropic on the 1, 2, 3 coordinate system. All right, so what do I mean by that? Well, here we have this. I'll do my best to make a cube of material. One, two, three axes. Okay, and so what it means to be orthotropic on the 1, 2, 3 axes, we sort of have to go back to remember what the definition of an orthotropic material is. And the definition of an orthotropic material is a material that has 3 mutually perpendicular planes of symmetry. Okay. In our derivations so far, we have assumed that the planes of symmetry are the 1, 2, 2, 3, and 1, 3 planes. Okay. And so we went through our derivation of the compliance matrix by assuming load in the one direction, which was like a principal axis. All right. So we would call these the principal axes, or the principal material axes. But in reality, you could have loads that are applied to some object that are not necessarily aligned with those axes. And we sort of talked about this in the past, is that you could have some random arbitrary coordinate system, which is kind of coming off here, which is like x, y, z, right? So this x, y, z is arbitrary. So what we'd like is, we'd like to be able to define this stiffness matrix and the compliance matrix, not necessarily in the 1, 2, 3 direction, but also in the x, y, z direction, in terms of the stiffness in the x direction, the stiffness in the y direction, and the stiffness in the z direction. So generally the idea is, if we have your compliance matrix S in the 1, 2, 3 coordinate system, or C in the 1, 2, 3 coordinate system, can we go to S in some arbitrary X, Y, Z coordinate system, or C in some arbitrary X, Y, Z coordinate system, to find things like what is the stiffness in the X direction? What is the stiffness in the Y direction? What is the stiffness in the Z direction? What is the Poisson's ratio, X, Y? What is Poisson's ratio, xz? What is g, x, y, etc., etc., etc.? Okay, so instead of talking about what is the stiffness in the one direction, we might want to talk about what is the stiffness in the x direction, which may or may not be aligned with some principal material coordinates. All right, so let's say I got fibers running all in this direction. Cool, I know what my stiffness is in that one direction. But what happens if I pull it in some arbitrary direction? I want to be able to define what is the stiffness in that arbitrary direction. Okay? Okay. So we're going to get to this. All right. But first, I want to kind of go through an example that's similar to sort of what you did on your kind of last homework. Okay? Okay, so let's go through this example problem. I'm going to put an example problem here on the screen, and we'll work our way through it. So populating stiffness and compliance of an orthotropic material is our example here. This comes from page 16 of your slide deck. Maybe I can see if I can lure my dog here in the meantime for another photo op. Okay, so you can find this example in the slides. Maybe not great to like fully copy all of this information down, but let's go through an example where we populate a compliance matrix. Here we're going to work with E-glass epoxy composite unidirectional. So this isn't necessarily orthotropic; it's more specifically transversely isotropic. Okay. So I'll bring that kind of in and out as we work through this. All right. So the idea here is we first will populate this Sij matrix, then invert to get your C matrix. And maybe we'll just do like a couple of entries here, just so we get the general gist. Okay. All right, so let's just run through a couple of these entries and make our way through. So for instance, if we want to populate the 1, 1 entry, we know that this is going to be 1 on E1. If we sort of go back to our example handout here, we see that the modulus in the one direction here, the longitudinal modulus, 41 GPa. So we'll work in GPa here. So here this S11 entry is 1 on 41 GPa. So if you calculate this out, you'll just get 0.0244, 1 on GPa. Can keep making our way through. S12 here. This is going to be, just to be consistent here, it's the same as S21 because we're symmetric. This is going to be the same as S13 and S31. And this is because unidirectional composites are transversely isotropic. This one we get here by Sij symmetry. And so visiting my equation sheet, this is like negative 2 over E1. I'm given most of these material properties, negative 0.28 over E1, which is 41 GPa. So I could tackle all the entries of this particular stiffness or compliance matrix S by calculating this out here as negative 0.00683. 1 on GPa. All right. So I'm just sort of working my way through all of the entries kind of in brute force fashion. Next, I'll calculate S22, which is the same as S33, because this, again, is transversely isotropic material. Which is why I have this additional relationship. And this here will be 1 on G12, or, 1 on E2. Just kind of jump the gun here. Which is 1 on modulus in the 2 direction for this particular composite, 10.4 GPa. So here calculating 0.0962. 1 on GPa. Okay. The point is we could make our way through all other Sij entries, which we now know in terms of engineering constants, right? So we go back to our problem. I'll just move this out of the way for just a second for those copying it down still. So in the problem here, this information is information of a composite that has already been fabricated, right? So a typical unidirectional E-glass epoxy composite. So we've already kind of gone through the micromechanical models to sort of determine what things are, like the modulus in the 1 direction of this composite, the modulus 2, modulus 3, etc. You can see here that the modulus in the 2 and the modulus in the 3 directions are the same, because if you think of your typical unidirectional composite, the 1 direction, which has the fibers, will have a certain modulus, and then the 2 and the 3 directions, which are sort of across the fibers, will be uniformly equal because it's a plane of isotropy. So we see that sort of manifest itself here. And so you can sort of understand that just given this information here, it's a transversely isotropic material because unidirectional composites are transversely isotropic. Okay, so that's how we're sort of allowed to simplify your compliance matrix. All right. So all in all, you could find all the Sij entries if you wanted to do that. And you would end up with the following. And you can sort of work through this on your own if you'd like to sort of verify some of the other entries of this Sij matrix. So here we have 0.0244 in the upper diagonal. Negative 0.00683. The 2-2 entry, 0.0962. The 2-3 entry will be different, 0.0481. And here we will mimic for the 3-3 entry. Gonna have a bunch of zeros in space over here. Okay. Now kind of my shear components, which are in the lower right-hand side. 0.286. This is one on G23. Here, this is one on G12, which is 0.233000233. Units here are all one on GPA. Okay, so this is all obtained from material information that we have about our unidirectional composite. For instance, this guy, remember, is like 1 on E1. Okay, this guy here is like negative nu 1, 2 on E1. All right, those are all just obtained from properties of the composite that we have. Okay, so that's that. We could invert this. To get C, because remember, your stiffness matrix C is the inverse of S. All right, you can do that in MATLAB or your favorite solver, whatever you want. Sorry if some people are still copying that guy down up there. And I'll just give you this stiffness matrix C here, just if you want to try for yourself. Okay. Here, this guy is going to be 44.5. The 1-1 entry, 6.32. 6.32. 13.8. 7.83. And here we have 0.5. And we have 4.3. Units here are GPA. 4.3 GPA. Wow. You guys wish. It's not even possible. Okay. So this is how you might populate S, the compliance matrix, and C, the stiffness matrix, using material properties of, let's say, a unidirectional composite that you might have at the ready. Okay, let's move on. Next, we're going to sort of move into some ideas that hopefully ring bells from 3005. And that is, what happens if we have no longer sort of this like three-dimensional, fully constructed stress state, but what happens if we have some assumptions about plane stress or plane strain behavior? And as soon as I say plane stress and plane strain, people start to cry. So yeah, don't cry. Checking your grades on Canvas. I don't use Canvas. I like your meme though. Okay. Now, most of the time when you fabricate composites, you're basically stacking like unidirectional layers on top of each other. All right, that's kind of like most of the time how aerospace grade composite materials are made. You have carbon fiber pre-preg that is unidirectional, and you're stacking it on top of each other, tape laying, put it in an autoclave, put it on top of a mold, and what you usually pop out with is some like thin structure. Okay, so what we're going to talk about now is simplifications that we can make to this like three-dimensional theory that we've talked about for thin structures. So let's go ahead and do that. So here we'll tackle a new topic, which is thin laminates. Others do, though. Heart is not like the others. Correct. I'm my own brand of crazy. Okay. All right, thin laminates. I'll say that, you know, most of the time here, or many times in application, these composites that we make are thin. And so it would be nice if we could come up with some simplifications to our three-dimensional theory so that we could have a little bit easier life. Okay? So I'll say orthotropic composite laminates are often thin. Not like me. Too many pizzas lately. And that's because it's like multiple layers of thin stacked prepreg, for example. So ergo, for example. I'm Latin, did you know? So if thin, we're going to assume conditions of plane stress. Stress states are approximated with plane stress conditions. So they're approximated with plane stress conditions. We usually abbreviated this as, this is abbreviated as PL sigma with a squiggly under it. PL stress, plane stress. And that's what I'm going to do kind of going forward. So we will assume out of plane stress is 0. So what do I mean by that? We'll assume out of plane stress sigma 3 is 0. That's what we'll sort of assume, that sigma 3 is this out of plane direction. Okay. Also, because we have plane stress with the out of plane direction being the 3 direction, having no stress components, then also the shear components of stress, things like tau 1, 3, which here we've called, with our contracted notation, we call this sigma 5. This is also equal to tau 2, 3, which is tau 3, 2, which we call sigma 4, all equal to 0. This is what it means to be in conditions of plane stress. Okay, so that really simplifies our situation. And sort of the picture that you want to have in your head here is, let's say we have a unidirectional thin composite. Okay. So the picture you kind of want to have in your head is, if it's thin, here we are with sort of our very thin, long composite. Okay, maybe something that looks like that. I am great artiste. Okay, so you got all your fibers here kind of at the cross section that you see sort of poking out here. And so if we were to put a coordinate system on this, maybe we'd have a coordinate system that looks like 1, 2, 3. So if you're looking at this particular composite and thinking about, like, harken back to your 3005 days, this element on the surface here, this element is in plane stress. And generally, if the material is thin, you would assume that more or less every single element that you could have in the structure is more or less on a surface, or can be represented by the surface element. All right. So in this situation, you would have something like sigma 3 equals sigma 4 equals sigma 5 equals 0. That's what we're kind of trying to show here. So if this is the case, you can sort of simplify your Hooke's law. And it becomes the following. Your strain vector equal to, we'll assume orthotropic. We're just going to stick with the orthotropic here. If we assume here that we have just stress in 1, 2, and 6, like this, you could sort of do the math here. And show that your strain vector would look like the following. Sigma 1 S11 plus sigma 2 S12, sigma 1 S12 plus sigma 2 S22. Here you have sigma 1 S13 plus sigma 2 S23. 2 zeros. And then on the bottom here, sigma 6 is S66. Okay, so we've simplified our life a little bit, and this is sort of like our new strain vector. Okay, and we only have epsilon 1, epsilon 2, epsilon 3, and gamma 6. So if we're in plane stress conditions, we only have sigma 1, sigma 2, sigma 6, and we have epsilon 1, epsilon 2, epsilon 3, and gamma 6. Okay, so now this is just 4 independent equations. Which is something like the strain in the one direction is sigma 1 S11 plus sigma 2 S22. Epsilon 2 here is sigma 1 S12 plus sigma 2 S22. All right, it's a mistake here. It should be S12. Epsilon 3 is sigma 1 S13 plus sigma 2 S23. And then gamma 6 is just sigma 6 times S66. So these are the only 4 equations now that you have for Hooke's law for generally orthotropic material. All right. So it would be nice if we could write these equations in a more simplified way. And we can. And that would be the following. And here we'll say that this is contracted Hooke's law for plane stress. Plane stress. And that is this. Epsilon 1, epsilon 2, gamma 6 equals to S11, S12, 0, S12, S22, 0, 0, 0, S66, which looks a little bit strange because this is a 3 by 3, but we understand that we're taking that gigantic 6 by 6 matrix and just condensing it down to this 3 by 3 matrix. So this is your contracted representation of Hooke's law for plane stress. So this has like all the in-plane components. If you remember, that sigma 6 is tau 1, 2. So we're basically looking at the stress and strain on a two-dimensional surface element of our material. This is like and you know, this might give you hearkenings back to your 3005 class when you looked at things that looked like this. Oh, my arrows. My hand is getting tired. Where this is like sigma 1, sigma 2, and you have shear stress that's in the plane. Where this component here is like your sigma 6. Okay, so we're basically looking at this two-dimensional surface element now and representing this guy with sort of this plane stress behavior. All right. So went a little bit over today. Sorry about that. we'll leave it here. Do not include the strain in 3 direction because it's out of plane. Yes, that equation still exists. Good point. Okay, so recall we still have that 4th equation for out of plane strain, which is this epsilon3 value. Remember, when we're in plane stress, we have 0 stress out of plane, but we do not have 0 strain out of plane. Okay, that's something you should have learned in 3005. And remember here that we drew this above, that your strain in the 3 direction, your out of plane strain, is sigma 1 S13 plus sigma 2 S23. So this equation still exists, even though it's not represented in our planar representation of the stress state. So thanks for that reminder, Jack. Don't forget that that guy generally exists. That's because strain in 3 directions still exists, even though the stress in the 3 direction does not. Okay. That'll be it for today. Thanks for coming.